Okay, hello everyone. Let's start. Um, okay, okay. 这个是 okay. So this is my syllabus of this summer course. You can find on the Tsinghua University's website. So I basically talk about deriving PDEs from many particle system, focus on mean field limit regime. I will explain this later. So more precisely, I will talk about quantitative methods. Quantitative methods for mean field limit problems. Okay, so basically, so there are several. The classical one. So I will briefly mention in lecture one, this lecture, and there are several new methods I developed with my collaborators. So one is the relative entropy. So recently, it's called modulated free energy. Okay. So on this syllabus, you can find on website, or I will send you after this lecture. Uh, I will basically talk about several papers. The first is the notes by Gauss. So this is the notes on the classical results on mean field limit. This is also the notes. Okay, for the results part, the new result part, I will focus on several results of myself. So this is the first one. The second one, you can find this on my webpage, and also the paper by Savia Savati with her student. Oh, not this one, right? This one. Okay. I will just start by talking about the plane of this short course. Okay. So in this lecture, lecture one and two, I will give the basic notions of this problem. So it's introduction. So and classical result. Okay, in particular, like in today's lecture, so I will talk about distribution stability estimate. Okay, so later, so from next week, maybe lecture 3, 4, 5. So I will talk about the three methods. So the new relative entropy method. So I developed with my collaborators, Pierre Emmanuel and Pierre Emmanuel, Japan. And the recent method, as I read before, modulated potential, so modulated potential energy. So this is a method developed by Sabati and Durings. And also our recent method combined with combined relative entropy and modulated potential energy. So I call it modulated free energy. Okay, so in the last lecture, so I will talk about some applications some open problems. Applications. Okay, so this is the plan. And so I will just start. If you have questions, you can stop me while I'm talking. Okay, okay. So let's briefly mention the field, right? The problem. So what is the problem? The problem we are considering. Okay. Okay, so I must admit all students, all people to join the meeting. I must check that. Okay. Okay. So so what is the problem we are considering, right? So the problem we are considering is following. So we want to derive effective equations from microscopic system. So we want to derive effective equations, macroscopic system. So if, for instance, microscopic systems can be represented by like n-particle systems, like ordinary differential equations or SDEs. And macroscopic system, sometimes you can represent it as a PDE. A PDE. Okay. So for give you an example, a very famous example is the following. Right, we can consider Newton dynamics. We can consider Newton dynamics given by the following. So xi is the position, vi is the velocity, and Newton's second law is just given by the following. So K is the interaction force. So K is the two-body force. So you can think here 1 over n is the mass. Okay, so this is just Newton's second law. And if we say n goes to infinity, so formally this n-particle system, I equals to 1, 2 to n, can be approximated by a very famous Vlasov type PDE. So here F is the probability density. So X, V, right, both in R3. And rho here is the macroscopic or spatial density. The spatial density. Okay. So in particular, right, if K, you hear K is chosen to be minus gradient phi, so phi is phi x equals to, let's say this. So Poisson kernel. So K, let's say here is positive or minus. So then K can either represent the gravitational force, so which is attractive, or it can represent Coulomb force, so which is repulsive force. Okay. So then if we choose K and this very particular, right, which acts like this, so when X is very close to 0, so then the macroscopic PDE, so then this PDE is called Vlasov-Poisson. People use this to study like plasma physics or large scale galaxy models. Recent years, this PDE is very popular. For instance, in the study of Leno damping by Moore and Villani. Okay, so this is called Vlasov-Poisson. So so the flavor of our program, our problem is the following, right? We want to starting from n particle system. We want starting from n particle system here, and we want to derive the macroscopic PDE from the particle system. So in particular, we will focus on the case, the situation. So K is singular. So in this lecture, in the first lecture, so we will focus on the case, the interaction is smooth. So classical result, so for classical result, so K is usually Lipschitz, so Lipschitz. And there are many results in 70s. In particular, we will talk about Dubushin's estimate. So, and many others, by many other people. Okay, and basically we follow the first. So you can find the notes by Gauss for this lecture. So we basically follow Gauss notes. So in the syllabus. So it's first 4 sections. Okay. So those are the classical results. So the convergence from particle system to PDEs, you need require K is Lipschitz or even more. And you can give explicit convergence rate. So which is called Dubushin's estimate. So, but if K is singular, right? So if this K, the interactions, two-body interactions is singular, so the classical result can work in some situations, but cannot work for a very singular interactions. So that's why we introduce new method to study the mean field limit problems. Okay, but let's start from basic notions in these lectures. If you have questions, just let me know. Okay. Okay. So let's start. But, okay. Let's start by talking about Liouville equations. Okay. So let's call this two examples of mean few PDEs. So let's starting by talking Liouville equations. So what is Liouville equations? Okay, so for simplicity, let's consider a very easy example, right? Let's consider one particle which has position x and velocity v, and those particle moves in a force field given by F. So the Newton's second law is given by the following. So x dot, so this is time derivative. So v dot equals to the velocity, so equals to the force field. This is external force field. Okay, so this is ODE. So this is ODE, Newton's second law. And we can write the evolution of the distribution function, right? So this is just one particle. But if we are interested in the evolution of the distribution function of this particle, so what is Liouville equation? So Liouville equation actually is just the evolution equation. Let's say evolution PDE for distribution function. Okay, so which is F. Let's just write xt, xv. So t is time, x is position, v is velocity. So let's say x is in RD and v is also in RD. Okay, for our very baby model, so what is the Liouville equation for this single particle? So let's just write this directly. So which is partial TF plus, so V gradient XF plus, so let's assume the mass is M. So M is the mass. So which is 1 over M. So divergence V F. So this is the Liouville equation. So for this one single particles, so how to derive this is just a chain rule and taking expectation. So let's, okay, how to derive this? So just to, so let's say we take a test function d, and we take the xt is a solution for this ODE, for this ODE star. So this is xt vt, and you use the chain rule. So you use the chain rule, right? If this is a stochastic system, you use Ito's formula. So you can get gradient xt vt dxt plus gradient v, so phi xt vt dvt. Okay, so then you're using the star, so you substitute the star here and taking expectation. So I will just give the sketch. You can check this, taking expectation. So for instance, so when you're taking expectation like this, so what's this, right? So this is just phi x v, so f t x v dx dv. So this is rd multiplied rd. Since f is the density function, is a distribution function of this particle. So when you're taking expectation, write it in the integral form, right? So you have this f. So then you can integration by part, right? Transfer all the derivative on phi to the derivative on f. So if you get this Liouville equation, if you get this Liouville equation. So you can check this. It's basically just taking a test function integration by part, taking taking a test function using chain rule, taking expectation and integration by part. Okay, so this is the very easy example of one single particle moving in an exterior force field F. Okay, so if we want to solve, so this is a first order PDE. So if we want to solve this first order PDE, so we want to solve this first order PDE. So usually we can use methods of characteristics. And those ODE is just a characteristic equation. The characteristic equation of the Liouville of this, the Liouville equation. Okay, so this is a very easy example. And so the solution and time t can be written as the push forward. So let's say xt vt of initial data x0. So if we give the initial data for the Liouville equation, so this Liouville equation, and we're using the characteristics which is given by the this ODEs. We solve this ODE, we get xt vt. So this is a map, right? This is a flow, characteristic flow. So this characteristic flow will give you a map. So this map depends on time t, right? It's called a flow. This flow maps the initial distribution F0 to the time t distribution of this single particle. Okay. Of course, here is easy, right? But let me just remind you the notion of Sharp. So let's say, so T is a map. So let's say T is a map from space X to space Y. So if we have a mirror mu here, and so mu is a probability mirror on X, or it can be just a Fourier mirror on X. So mu, Fourier mirror on space X. So what do we mean by T star mu? So T star mu is a Fourier mirror on Y, right? So if mu originally is a probability mirror, right? So T sharp mu is also a, so T push forward mu is also a probability mirror on Y. So we define this push forward mirror as the following. So A is a set in Y. It's a mirrorable set in Y. So the size or the mirror of this set A in Y is mirrored by its image in the space X, mirrored by the original probability mirror mu. So this is a definition of push forward mirror. It's very useful to note the following formula. So let's say we have a test function phi, which is integrate on the space Y. So T push forward mu is a probability mirror on Y. So by the definition of push forward map, a push forward mirror, so this equals to phi compose T x d mu x. This is another form, right? This is another form of change of variable. So, but it's very useful. We use this many times, and this is right. Some people might doubt the validity, right? Because there's no determined term of this mem t. But actually, this is true. This is definitely true. And we will use this several times later. Okay. Okay, so this is a very easy example. But sometimes it's not that easy, right? So let's just excuse me. Okay. Okay. So this is a very easy example, but sometimes it's not that easy, right? Because here here the exterior force field, right? So this is exterior force field F, right? This is just a given. But sometimes this is not it's not that easy. Sometimes the force field will depends on the distribution of particles. So let's just use this example again. Vlasov-Poisson. I just want to give a very formal derivation of this Vlasov-Poisson system. So this is like physical way of derive PDE, the Vlasov-Poisson system. Let's just write here. So this is F is the phase space density. Oh, excuse me. So F is the phase space density. Okay, for simplicity, so now, so let's just consider the 3D case, right? Just the 3D, right, in our physical space. Okay, so the usual way to write the Vlasov-Poisson system. So this system describing like so the plasma physics, plasma, there's a plasma. So V gradient XF. So this is E. So let's follow the notion in my notes. So okay. So, okay, let's first write euro way. Okay, so this E is a electric field. Electric field. So it usually is gradient minus gradient phi, and phi so is given by rho f. So rho f is where, right? So where rho f is a macroscopic density. So f t x v. So we integrate with all velocity variables, so we get a spatial density. Okay, so how to derive this? How to derive this? Let's just using a physical way to derive this. So because here this actually is the force field, right? So E is the force field. So this force field is generated by the distribution of all particles. So we call this force field F. We call this E self-consistent force field. Okay, so let's just derive this. Okay, so by Coulomb's law, if we have a particle, if we have a charged particle, let's say ion or electron particle charged, so with mass m and charge, which is q. So if there are two particles, so if there are two particles, so one particle is at this position, so another particle is at y, right? It's under y. So we want to write the formula, right? So what is the force generating and point x, right, from the particle y? So the Coulomb force exerted on the particle, on such particle and position x by another particle from the position y. So which y should not be x. So what is Coulomb force here, right? So Coulomb force is also called electrostatic force. So which is repulsive force. So the force which is Q squared, right? So it's the product of the charge of both of those particles. And this is just some physical constant, which are not very important. And this is the Coulomb force, which is also square reverse law, right? So which acts like 1 over x squared. So x is a distance. So this is a part the Coulomb force x and point x from particle and position y. But sometimes we are interested in the distribution of particles. Let's say there is a distribution of particles which is here. So the density is rho. So then what is the force generating like from a cloud of particles? Okay, so let's say if we have a cloud of particles, and with those particles with a density function rho ty. So what is the force and point x now, right? So we just write the force and point x, the Coulomb force. So we should be this. So we just integrating all the distributions, right? And each in infinitesimal point, right? So that's it, right? And this looks very familiar, right? So if we take phi, so this can be written right in the potential form. So this actually is a gradient of some potential. Excuse me. Okay. So if we take phi, right? If we take phi x to be the fundamental solution to the Laplace equation in 3D, right? Which is Poisson kernel. So then, so we can, so, okay, so this is a fundamental solution to the Laplace equation in 2D, in 3D. Okay, so we can write this force field Fx as Q, right? So here we consider some physical constant, right? So, but when we study mathematically, we basically throw all those terms away. So we can write F as QE. So E is the electric field. And so E, Tx, the electric field can be written as a negative gradient of some potential. So phi is the electrostatic potential. So now, so if you take the divergence of E or take the Laplace of phi, so we can get the equation. Okay, so let's write. So here actually, so you don't need to check this. So let me just write this out. So phi tx, so actually equals q over epsilon 0 is just physical constant. So f rho tx, and you can check if we take e as the gradient of phi, which gives it exactly the same form. Okay. And now you take the gradient, you take the Laplace phi, so you will get just this q over epsilon rho tx. So this formula and this is E. And now the Liouville equation combined with this. So thus, Liouville equation with E is F equals to Q E. So then gives us Vlasov-Poisson. Gives us Vlasov-Poisson. So here, right, you can see, right, so this electric potential is generated by the distribution of all particles, which is rho. So in the end, right, so the force field is self-consistent. Okay. Okay. Yeah, so that's the first model. That's the first example I want to say. So there are many studies of there are many works on Vlasov-Poisson system. So for instance, right, recently there's many works on Lenoir damping. Okay. So it's still open nowadays, right? It's still open nowadays to derive from the Newton dynamics to Vlasov-Poisson. So in the mean field, limit. So which is just I said in the very beginning. So we take the kernel K, we take this kernel K as this form. Some constant. So in 3D. So this is still open. Okay. The second example I want to say is, let's say second example. So is the 2D incompressible Euler equation in vorticity form. Okay. So Euler equation is very famous, right? So people say this is the first PD, maybe second, ever derived, ever written down in the history. So what is equation? Right. So let's just write this down. So which is partial Tu plus U gradient X U okay plus gradient XP so Tx equals to 0, divergence U equals to 0. So here U actually equals to U1 Tx, U2 Tx, so which is the velocity field. So any questions? Okay, so U is the velocity field, and P, so which is scalar, so is pressure field. So P equals to PTX. So this is scalar. This is pressure field. So everything, so here X is in R2. So it's 2D incompressible Euler. So if we check, right, so if we just write in this way, right, you cannot see the 2D incompressible Euler equation as a mean field limit of some particle system. So you can only see that when we write the vorticity formula, write a 2D Euler equation in vorticity form. So how to do that, right? So we take So we take omega, which equals to omega Tx. So which is the vorticity. So this is vorticity field. So vorticity field, right, in 2D actually is just a scalar. So if you multi-D, right, in 3D it's a vector, but in 2D is just a scalar. So which is defined as this. So nabla perp U1, U2. So this is a rotation. So this is a rotation of the Euler gradient. So you write this out. This partial x1. So U2. So Tx minus partial x2. So U1 Tx. Okay. So if we take the perp, we take the rotation of nabla. So we can just apply this operator on the first equation. So we just apply. Sorry. So we can just apply perp, the gradient perp on the first equation, and we can derive the evolution equation for the vorticity. Okay, so we can just get the vorticity. Just to get this. And of course, right, so here the divergence U is free, and U, I will skip this, but so U can be represented by the omega as well via a stream function. So basically it looks very familiar with the previous discussion, right? But here it's not exactly the Laplace equation, but there's some rotation. So there's some rotation. But anyway, so U can be written as the integral, the singular integral of omega. So UTX, so actually is equals to something like this. So let's just using a very simple way. So K convolve omega. So omega depends on T, right? So here is X. So this K looks like the following. So X is in 2D. So Kx is the very famous Beer-Savart kernel. So X perp actually equals to, I'm not very sure the sign, but let's just use this. So yeah, so Kx is Beer-Savart kernel. So there might be a difference of the sign, but yeah. So this is the Beer-Savart kernel, which is also singular. So we will talk about this in next week. So the derivation of 2D Euler and Navier-Stokes from particle model, vortex model. So we'll talk about this in next week. Okay, so this is a second example, right? So if I rewrite this equation, so if I rewrite this equation here, so what's this equation, right? So the vorticity form is the following. So U now is the convolution of K with respect to the vorticity. Okay, so of course here vorticity is not necessarily positive or or probability density. But we can still think, right, this as a limit of interacting particles, right? So we can write this as this. So xi. So if, let's say, if omega is positive and omega is a probability density, so the 2D Euler equation can be think at this formally, right? And we can show that rigorously later as the scaling limit, as the mean field limit of the particle system. So, and here the K, so here the K is just the interaction kernel. K is just the Beer-Savart kernel. So this kernel. Okay. So this is a second example, which is solved now, and I will give you detailed presentation in next week. So there's another example. So let's say, let's call it Petlek, Keller-Seeger. I will just briefly mention this. More details will be given later. So this is a chemotaxis model. So what does this mean? We have a bunch of particles or some chemotaxis or some bacteria, right? And those particles emit some chemicals, and then those particles are attracted by those particles. So those particles move towards the region has high concentration of those particles, of those chemicals. Okay, so if we formally write the dynamics, so what's this, right? So it's first order model is we just have position and not a position and velocity. Is the first order model, so which is given by the following. So those particles are interacting by each other. So the formula looks like exactly the form before this, but the kernel is different. So here I equals to 1 to n. So what this is, this kernel K. So this kernel K is a Person kernel. So phi, let me just write the exact formula. So Kx actually equals to minus, there's constant which depend on d, and x over xd. So this is attractive force. So those particles are attracting with each other, and the interaction force is singular. So usually d bigger than 2. So which actually is gradient of phi x. So phi, I think phi this like this. So phi is a Person kernel. Or phi phi is the fundamental solution in dimension d. Okay. If we take formally take the mean field limit, which is, so then the density, let's just write now for the time being, the empirical measure of those n particles. So this is called empirical measure of those n particles. Oh. Okay. So those empirical measure of particles will converge to some density function. Let's just call it rho. But the convergence will be made precise later, right? So it's the main topic of our of this lecture series. So rho t x. So rho t x will solve the famous Petlek Keller-Seeger systems. So partial t rho plus some divergence rho. So here is k convolve rho. So that's not just this, right? Usually, right, when people modeling this, there's also some diffusion effect. So people add some factor here. So let's just consider easiest case. Let's say this is square root of 2, and then usually add some Brownian noise. So those particles, those chemicals will diffusion as well. So as n goes to infinity, so formally people expect the convergence in some sense of empirical measures towards the density function rho. So here is just the Laplace rule. So this is Pedelec Keller-Seeger PD. Okay. In the last part, so maybe 2 weeks later, we will talk about the quantitative result of the convergence from empirical measure mu n towards the solution of rho. And again, right? So here, right? So this is u. This is u. So u is velocity field, and you can think this u as the self-consistent velocity field. And this u, right, which is k convolve rho, is a formal limit of the right-hand side in the ODEs. Okay. Yeah. So any questions? So if no, I will go to the next part. So this is all I want to talk about, the examples. So all those we will mention later. Okay. 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 So now let's give the general framework for the classical result for mean field limit. Okay. Okay. So let's just call this stability distribution. Distributions estimate. Okay. Okay. So let's give so this is the first result we'll present in full details. So even nowadays, right, when you try to derive PD rigorously from particle system, so this is the first method you can try. It works for many situations, right, even for some singular cases. So it's the very classical. So I think it dates back to 70s. So I will just present this first. Before that, we need a good formulation. So before, we already write this formula several times. Right, we already write this first order ODE several times. Okay, but people might ask, so why do you put this 1 over n there? So what does this 1 over n means, right? So this 1 over n is usually obtained by change of time. So let's say, okay, let's say if we consider, so what's this? What's 1 over n? So this is called mean field scaling. Okay, so this is the for first order system of O. So this is usually starting point of mean field limit. So this first order or second order ODEs. So we usually write, so there's a time derivative. Okay, so VI equals to Right, so this is Newton dynamics. Newton's dynamics. Okay. So what does this 1 over n means? What does this 1 over n means? So let's just focus on the first order model, first order ODEs, or the second order ODE. So this. So you can write zi. You can introduce a new variable zi as xi vi. So you can rewrite the second order ODEs, right, Newton dynamics, in a similar form, but not exactly the same ODEs like this. So in the following, we introduce a general formulation, so which is adopted by Gauss in his notes. So we use a uniform notion, we using zi to denote the phase space coordinate. So let's use zi, so which can be xi in the first order model, or it can be xi vi for the second order model. So zi is the coordinate in phase space. So this is a phase space coordinate. Okay. So now, right, so if we can write the interaction kernel or interaction force, right, as the following. Interaction kernel K. So we write the interaction kernel K like the following, is from RD to RD. So like K, Z prime. So Z is one coordinate, Z prime is another coordinate, right? So Z is, let's say ZI, Z prime is like ZJ. So KZI, ZJ represent the interaction between ice particle and J's particle. Okay, so usually, right, if we just write, so if we just write the evolution equation, right, so it can be the following, right? So Zi, the time derivative, equals to J, right, usually, so the ice particle feels interaction from all other particle. So J is not equals to I. So J from 1 to N. So K, Z, I, ZJ. So this is a usual modeling, right? The usual way to write the equation. So, but the problem is if we just study this system itself, sometimes you cannot get, I mean, you cannot get a very interesting behavior because, right, if K is all in order 1, right, so this will be very big, right? If K is in order 1, so here we have n minus 1 term in the summation, so the right-hand side will be very big. And you cannot expect very nice scaling limit behavior. So the usual procedure is, okay, so we change our time variable in order to keep the total interaction, right, x and the particle I to be in order 1. So there's a question. So there's a question from Guixiang, Xu Guixiang. So
我有个问题就是，你左边 ZI 是 2D 的变量，你右边变。
It's the same. Okay, I know your question. Yeah. So so you probably wonder, right? The dimension is different, are different in both sides. So actually they're the same. So Zi is in ZD. So Zi, sorry. So Zi is in dimension D. So K actually is, so you have two variables, right? But the output is in RD, right? So K is also in RD.
Thank you.
Yeah, thanks. Okay, so the usual idea, right, is to do the time changing. So somehow, right, so do time changing, change of time, right? Maybe change of time, like change of time. Okay, so you can check this. So if you check t, so here so this is just a dzi over dt. Okay. So if we change the time, so let's say if we change t hand equals to nt. So what does this mean? So original time. So 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 if we do this time change, right? If we change time from t to t hand, so then now if t hand is in order one, right? If t hand, the new time variable is in order one, so then the original time t is in order of 1 over n. So when you do the change of time, so you can do the computation, right? So dzi hand, so dt hand, right? Using the change of using chain rule, right? So we get so dzi over dt over dt hand. Dt over dt hand, so you get 1 over n dzi over dt. So now we get 1 over n. So j is not an I, so kzi zj. So this is a formula we used. And this is the starting point. So from now on, you can think this for a while, but people argue, some people say, right, the mean field scaling is just some very short time behavior. That makes sense. So if you, after you do the change of time, so we can put 1 over n before the summation. So from now on, we can just write the ODEs. Just write the ODEs for the phase space state Zi as the following. So J is not I. So J is sum from 1 to n. So K Zi Zj. So we write like this. So I equals 1 to n. So from later, we just starting from these ODEs. But of course, right? So actually, in my work, we consider stochastic systems as well. So sometimes we add extra stochastic terms like sigma n, dwti, or some degenerate noise. But you can just ignore the stochastic part now at least. Okay. I want to be a little bit quick, but you can read both notes for details. So I want to skip a lot discussion on the Wilcoxness of these ODEs. Okay, so let's do some assumptions. So this is assumptions for almost all classical works, but it might be even stronger, but let's assume those assumptions. So all the later discussion in this lecture, so all assume these assumptions on K, on the kernel K. So let's make some assumptions on K. So the first one is this K is skew symmetric. Is skew symmetry. So what does this mean? So it's like z prime. So if we interchange z and z prime, so you get a minus signs, get a minus sign. So So this is basically the Newton's third law. It's not a very strong assumption. So Newton's third law of motion, basically also called action-reaction law, is something like okay. So if two particles they have interaction with each other, so let's say this is the x y, right? This is F y for x, right? The force from y, x on x. So this is the force from x to y. So Newton's third law says these two forces and the vector, so they have different sign, right? So basically this, right? This is not very strong assumptions. Okay. So from skew symmetry, right? If K is skew symmetric, if we take Z equals to Z prime, so actually we can get Z equals to 0, right? You can say, right, so no self-interaction. No, this is band words. Okay, so let's forget that. So which tells us, right, KZZ, right, equals 0. So if K is defined everywhere, so if K is defined everywhere, right, so on the diagonal, so K vanish. So this is the first assumption. The second assumption is, let's see, is K is Lipschitz. So basically says K is Lipschitz. K is or so let's say K gradient Z Z prime is a gradient Z prime K Z prime is less than L. Is less than L. It's something like this. Okay, so it's like K is globally Lipschitz, and the Lipschitz constant is like just L, right? And so after, we can make this assumption. It's basically the same. C1 is C1. Okay. So under these assumptions, I will just Thailand, right? So it's a very classical work. So the well-posedness of ODEs about. So under the Lipschitz assumptions of the kernel K, right, which is the force field, so the ODE is globally well posed. So you can exchange the solution. Another remark, sorry. So K is globally Lipschitz, right? So the derivative, right, is bounded by L. So since the derivative is bounded by L and K is also vanish on the diagonal, so actually K grows and least linearly. So let's write, sorry. So actually K grows linearly. So from 1 and 2, from assumption 1 and assumption 2, so K grows at least and most linearly when Z or Z prime goes to infinity. So this is a direct corollary from our two assumptions. So, right, by Cauchy, so this is the classical theory of ODEs. Oh, sorry, it's Cauchy-Lipschitz. By Cauchy-Lipschitz theory, so we have the well-posings of the ODEs. And moreover, right, and moreover, we have the well-posings of the mean field PD. So, but I need to write this explicitly. Okay. Okay. So, okay. So first, the original equation. So a remark. The original equation, which is like this. Oh, sorry, Zg. So now, since k vanish on the diagonal, right? So we can write as the following. Right. So we can just add the diagonal terms. Right. So we just write this formula. Okay. Um, okay. Okay. So let's just write all the classical results, like Cauchy-Lipschitz theory for the well-positiveness of the ODEs and the mean field PD. I will write then what is the mean field PD, which is basically the limit we want to derive has well-posed, has unique weak mirror valued solution. So this can be proved by the Euler method, right, in ODEs, like a Picard iteration. So I will just write the statement of the theory and use then to get the distribution estimate. Okay, so this is first theory. Basically, it's just Cauchy-Lipschitz. You can adapt the proof, right, in the Cauchy-Lipschitz theory to give the proof of the following theory. Okay, so under all assumptions above, we have the following. Okay. So first, for each n is bigger than 1, and the initial data for each n tuple so this is initial data. So the Cauchy problem for the ODEs, right, above with initial data given has a unique solution, has a global unique solution. So this solution are time differentiable. So which we write as the following. So which is the push forward. So TT is the flow of the initial data. Okay, so this is just the exactly the same formula, right, in the classical Cauchy-Lipschitz theory. And also the following, the empirical measure. So the empirical measure is just defined as the sum of Dirac's given and the positions of those m particles. So which is mu t z n I. So which is defined 1 over n, or sum over all particles, each one with mass 1 over n. So here is j equals 1 to n I. Let's use I. So delta, so that's just z I t, z I t. So this is empirical measure. Those empirical measure is a weak solution. Of the Cauchy problem. For the mean field PDE. So the mean field PDE is just the PDE we want to derive or we want to compare to. So here is just kappa f. I will define this kappa, this kf letter. K is the operator. So initially have probability f initial. So f initial is just given by the initial empirical measure. Okay. So this is just another way to write the part A. Yeah, so you can check this directly, but this theory tells us. So when k is Lipschitz, or under those assumptions for k, right? Basically, when k, the interaction k is Lipschitz. So when k is Lipschitz, the ODE is basically the same as PDE. So the empirical measure for the ODE systems solve the mean field PDE exactly. So this is not true later for other type of convergence. But if we add noise there, so the empirical measure does not solve the expected mean field PDE exactly, but here it solves the mean field PDE, right here, the mean field PDE, let's say MFD exactly. Okay, so this tells us, right? So this tells us, right? So let's say we can just study, right? This hints us, we can just study the stability. Oh, pardon me. So here note kappa f. So kappa f is defined as the following. So Tx, so kappa, sorry, it should be z prime f t d z prime. So f here is a probability distribution, a probability density, or even just a mirror, a probability mirror. So kappa f looks like a convolution, right? If we choose k, so if we choose k z prime, like k z minus z prime, so then here is just a convolution. So then, so it's small k convolves f. So then it's just a convolution, right? But here is also some integral type operator, right? Okay. So here, right, since the empirical measure solve the mean field dynamics, the mean field PD exactly, so this hints us we can study the stability. So we can just study the stability of MFD directly. Okay. So, and this is just the Dubrusian estimate. So the Dubrusian estimate says, right, so we just studied this. We just studied the mean field dynamics. And given different initial data, let's say F initial 1, F initial 2, and we can control the growth of the distance between F1, right, solution to the first initial data, F2, the solution to the second initial data. So we can control the groups. So in particular, right, if we choose F1, so if we choose, maybe just, I just write this exactly. So this is just a distribution estimate. So the idea is the following, right? So let's say if we can control the growth of Ft, so this is the one Wasserstein distance we will define later, but the distribution estimate says exactly the following. We will make this precise later, but this is the basic idea. Okay, basic idea. So 2LT W1 F1 initial, F2 initial. So this is the distributions estimate. So given two initial data, F1 initial, F2 initial, we can control the growth of one Wasserstein distance. Okay, this is a stability estimate for the mean field PD, right? So this holds for all initial data, right? But of course, we need some condition to make sense, make those works, right? To make this reasonable, right? Okay. But anyway, this works for general probability measures, not just for densities. So now if we choose, this is our target. Let's say if this is our target rho, and this is our density, this is our empirical measure mu n initial, okay? So this is our target, let's say rho initial. So we can have the estimate, right? Immediately, we can have the estimate immediately. So rho 1 t, right? This is our target, the solution for the mean field dynamics. And so this is the empirical measure for n-particle system. So by the distribution estimate, we can directly obtain a mean field limit. Right. So as long as initially, right? So if so this converge to 0 if initially, so W1 initial as n goes to infinity, right? If initially the empirical measure of those particles approximate a target rho initial, so then we can propagate this distance, right? So we can get a mean field limit, right? So this is mean field limit. Okay, so then said, right, distribution estimate, so implies directly. Okay, so that's the strategy, but the all here, right? So what we need to do, right, is to establish the following, right? So to establish this, okay, we have maybe like 3 minutes, and I can answer your questions, and maybe I just stop here and answer your questions. From next time, we can give the estimate, give this estimate. Okay, so any questions? You can unmute or. Okay. Yeah, maybe I go on. Okay, does the estimate holds for all the examples you give at the very beginning of the lecture? Yeah, if it holds, that's that's the dream, but usually it does not hold. Yeah, so it only holds for very like Lipschitz case. In general, this is not true. Yeah. Okay, Zebang asked a question. Can we tighten the estimate where s is the longest distance a particle travels as t goes to, where s is the longest distance particle travels as t goes to infinity. E to s. I'm not sure what s here means. S is the longest distance. I'm not sure. I'm not sure. Yeah. So here, actually this Dubushin's estimate is very, I mean, it's very straightforward or trivial estimate. You can say it does not use any information of the dynamics. It's basically just maybe I will say that in the at the very beginning of next lecture. So it's basically just so if you have two ODEs, right? Let's say X is one solution, Y is another solution. It's basically just you compare the divergence of these two solutions as t grows. It's very rough, it's very straightforward estimate. So it does not consider any information of the dynamics. So so it holds for all the situation. It holds for all situation when the kernel is Lipschitz. Yeah. Yeah. So if you have questions, if you don't have questions, so maybe we stop here, or I hold this for several more minutes. So yeah. So but I won't talk new things. Okay. So maybe I just stop recording, and if you want to ask me more questions, so you can. Okay, so Sebastian asked, so if K has higher order smoothness, does it help? Okay, that's a good question. So if K has a higher order smoothness, yeah, I'm not sure. I don't think it will be helpful. Yeah. Um, yeah, I don't think so. Unless maybe not a high order smoothness. So if K, let's say, so if the kernel, you can write the kernel in some specific form. Let's say if K is has some convexity property, maybe you can improve this. And sometimes you can even get a uniform in time estimate. There are actually several works in that direction. But maybe you need noise or some other things, maybe not just like specific this form. But there are several works in that direction. If K has some convexity property, maybe not just a C2, C3, then that can be helpful. And sometimes you can get a estimate which holds uniformly in time. So for Dubushin estimate, right, if we look at the Dubushin estimate, so when the time is in log scale, so the estimate will be useless. So the time actually is small. Yeah. Okay, so ABC ask, does the uniqueness hold? What do you mean uniqueness? Okay, so if you mean the uniqueness of ODEs, that's an issue. So for instance, because if K is Lipschitz, we have the Cauchy-Lipschitz theory for ODEs. So we can always, right, I mean, we can always have the uniqueness and list for the flow. But if K is not Lipschitz, sometimes even singular is not an easy issue. It's not an easy question. Yeah. Yeah, so later I will talk about our approach. So we didn't really use the flow point of view of ODE systems. We used the Liouville point of view, a statistical point of view. We write the ODE system as in the sense of distribution, right? We studied the evolution of the particles. So we can give the meaning of the distribution of n particles. But this does not mean, right, we can give exact classical meaning to the ODE system. We even don't have uniqueness in some situation. Yeah, so the uniqueness or well-posedness of ODEs given, let's say, given some singular interaction kernels K is not an easy question. Right? So our chair, Jinxin Xue, so he's an expert of dynamic system. So I mean, even for full body problem or five body problem, so you can, let's say if you consider the gravitational interactions, you have very weird, very complicated behavior. Yeah. So Zhu Wangchan, so do you derive 3D Navier-Stokes as a mean field limit? Oh, that's a good question. But 3D Navier-Stokes. So 2D, right? We can do 2D, right? So because for 2D, we can write 2D Navier-Stokes as a vorticity form. So so it's we can use, right, formally, right, you expect that's true. But I'm not sure, right, how to write 3D Navier-Stokes as a mean field. Yeah, I mean, yeah, I don't know.